Hello and welcome to the AI Research Roundup. I am Alex. Today, May 11th, 2025, we're looking at an ICLR conference paper, Proxy Denoising for Source-Free Domain Adaptation, published a bit over 3.5 months ago. This paper tackles source-free domain adaptation, or SFDA. That's where an AI adapts to new, unlabeled data from a different environment, crucially without its original training data. The authors find that vision language models, or VIL models, which link images and text, can give noisy advice here, so they propose a proxy denoising method to fix this. Alright, so this first figure gives us a conceptual illustration of their ProDe approach. We see the in-training model on its adapting path from the source domain. The key insight here is leveraging a proxy vision language model space, which approximates the ideal latent domain invariant space. A latent domain invariant space is essentially an abstract representation where data features remain consistent, regardless of their original domain. The figure highlights a proxy error between these two spaces. ProDe then applies a proxy error correction, adjusting the adapting direction towards a more desired adapting direction, ultimately enhancing model adaptation. Building on that idea of proxy error correction, these diagrams dive deeper. On the left, they illustrate the dynamics of this proxy error. Initially, as the model adapts, the error between the vision language model's guidance and the ideal adaptation path is small. But as adaptation progresses, this error can grow, making the vision language model's predictions less reliable over time. Then, the right side shows how ProDe capitalizes on this understanding. It applies proxy denoising directly at the logit level. Logits are the raw scores a model produces just before they're converted into final probabilities, and then uses mutual knowledge distilling regularization, a technique to encourage consistent learning between the corrected guidance and the adapting model. Okay, so to see how this proxy denoising and mutual knowledge distilling regularization performs in practice, this table shows results for closed-set source-free domain adaptation on the Office 31 dataset. Now, closed-set source-free domain adaptation means the model adapts to new data where the object categories are the same as its original training, all without accessing that original data. The Office 31 dataset is a standard benchmark here. ProDe V, their method using vision language models, achieves the top average accuracy of 92.6%, just ahead of other approaches like default versus on this specific benchmark. This supports the benefit of correcting those noisy vision language model predictions. Following those Office 31 results, this next table, Table 4, broadens the comparison, specifically looking at results with the CLIP vision language model. It compares ProDe R and ProDe V, which are their methods using different CLIP image encoder backbones, against the standard CLIP R and CLIP versus versions. Across all listed datasets, including Office Home, VizDA, and the challenging DomainNet 126, ProDe consistently achieves higher accuracy. For instance, on DomainNet 126, ProDe V reaches 85.0%, a notable improvement over CLIP versus 76.3%. This pattern really underscores the effectiveness of their proxy denoising approach when using vision language models for domain adaptation. Expanding on those strong results, Table 7 now explores ProDe's performance in even more complex scenarios on the Office Home dataset. We're looking at source-free multi-target domain adaptation, or SFMTDA, where a model adapts to several new target domains simultaneously. Then source-free multi-source domain adaptation, SFMSDA, which adapts to a target using knowledge from several now inaccessible source models. And finally, test-time adaptation, or TTA, adapting on the fly to new incoming test data. In all of these challenging settings, ProDe V, or its ensemble version for SFMSDA, again leads, achieving 83.6% average accuracy in SFMTDA, 85.0% in SFMSDA, and a notable 76.5% in TTA, showcasing its broad applicability. Alright, to really pinpoint what makes ProDe tick, Table 8 presents an ablation study, where model parts are altered to see their individual impact. The top rows focus on two key loss components, using both the loss for maximizing mutual information, or L-apartment, which promotes agreement between denoised vision language model and target model predictions, and the pseudo-labeling loss, or LREF, based on those denoised predictions, together yields the best average accuracy of 89.3%. The lower rows then show removing the proxy denoising mechanism, or just its logit-level correction, significantly lowers performance, confirming each element's importance. So, building on how each component contributes, Figure 4 visually analyzes the proxy denoising dynamics. Subplot A uses maximum mean discrepancy, or MMD distance, a measure of difference between data distributions, to illustrate the target model's feature space converging towards the proxy vision language model space. This convergence is important because, as their theory suggests, the proxy's reliability decreases as this distance shrinks. Then, subplot C shows ProDe with its denoising achieving higher accuracy throughout adaptation compared to simpler methods, highlighting the benefit of correcting those increasingly noisy proxy signals. So, to wrap up our look at proxy denoising, the authors clearly tackle the noisy predictions from vision language models when used for pseudo-supervision. That's creating temporary labels to guide learning, especially in source-free domain adaptation, where models adapt without original data. ProDe's innovative proxy denoising mechanism, with mutual knowledge distilling, helping align model understandings, shows significant gains. It's a compelling solution for these tricky adaptation scenarios. That's all for today's AI Research Roundup. Thanks for tuning in. I'm your host, Alex.